Welcome to our exploration of linear algebra fundamentals. Linear algebra is a branch of mathematics that deals with linear equations, vector spaces, and linear transformations. At its core, linear algebra involves understanding and solving systems of linear equations. These take the form of a1x1 plus a2x2 plus anxn equals b. Vectors are fundamental building blocks in linear algebra. They are mathematical objects possessing both magnitude and direction. These vectors reside in vector spaces, which are sets of vectors that can be added together and multiplied by scalars while remaining within the same space. When we add two vectors from the space, the result is still in the same vector space. Similarly, multiplying a vector by a scalar also yields a vector in the same space. Matrices are rectangular arrays of numbers that serve as powerful tools for representing linear transformations. Key matrix operations include addition, multiplication, inversion, and transposition. These operations allow us to manipulate and solve complex linear systems. Linear transformations are mappings between vector spaces that preserve vector addition and scalar multiplication. Here we can see how a matrix can represent a linear transformation. In this case, our matrix stretches the space in the x direction by a factor of 2. Linear algebra includes several advanced concepts that provide deeper insights into matrices and transformations. Eigenvalues and eigenvectors are special values and vectors that remain parallel to their original direction after a linear transformation. The determinant is a scalar value that represents the scaling factor of a linear transformation, indicating how areas or volumes change. Singular value decomposition, or SVD, is a powerful matrix factorization method that generalizes eigendecomposition to non-square matrices. Linear independence is a crucial concept that describes a set of vectors where none can be expressed as a linear combination of the others. In this example, these two vectors are linearly independent because they point in different directions, and neither can be expressed in terms of the other. In contrast, these vectors are linearly dependent because one vector is simply a scaled version of the other. We can express the blue vector as twice the red vector. Let's summarize the fundamental concepts of linear algebra we've explored. Understanding these fundamentals is essential for grasping the power and versatility of linear algebra in various applications. Linear algebra is not just abstract theory, it's a powerful tool with applications across numerous fields. In image recognition, images are represented as matrices, and linear transformations are used for operations like rotation and scaling. Natural language processing utilizes linear algebra for word embeddings, enabling mathematical analysis of text data. Control systems in engineering rely heavily on linear algebra for modeling and design. System dynamics are represented using state space equations with matrices. Data science leverages linear algebra extensively. One key application is dimensionality reduction through techniques like principal component analysis, which reduces the number of variables while preserving important relationships in the data. In medical imaging, linear algebra enables efficient compression of clinical images through singular value decomposition. This reduces storage requirements while maintaining critical diagnostic information. Looking ahead, linear algebra is becoming increasingly important in several emerging areas. Let's explore the key future trends that are shaping its evolution. As we've seen, linear algebra has evolved from an abstract mathematical theory to a cornerstone of modern science and technology. Its applications span numerous fields, and it continues to drive innovation in computation and analysis. Linear algebra is not just a subject of academic interest, but an essential tool that powers the technologies shaping our future.